Hello students, welcome to EPG Pathshala. I am Dr. Ayushi Paliwal from University of Delhi. So students, today we are going to discuss about the module Semiconductor Nanoparticles and Optical Transitions in Semiconductor Nanoparticles from the paper Physics at Nanoscale. So the learning objectives of this module are: first, we will discuss the top-down approach, that is nanoparticle as a small crystal. Second, the bottom-up approach, nanoparticle as giant molecule. Thirdly, the effect of quantum confinement on optical transitions in nanoparticles. Next, we will also discuss the absorption and photoluminescence spectra of semiconductor nanoparticles. Lastly, the dipole moment and optical transitions in nanoparticles will be discussed. So students, let us start with a basic introduction about the module. Semiconductor particles of nanometer size, they are referred as nanoparticles, nanoclusters, nanocrystals, quantum dots, etc. All these names are used almost synonymously except the nanoclusters, which sometimes refers as extremely small particles whose properties have similarities with a molecule. So the term nanoparticle NP is most popular and general one and refers to semiconductor particles with sizes between 1 and 10 nanometers. So they represent a system lying in the transition regime between the bulk solid and a molecule, and important for studying the novel properties of matter, generally described by the term size quantization effect. So the energy difference between the ground state and excited state in an atom, equivalently energy differences between the highest occupied molecular orbital, HOMO, and lowest unoccupied orbital, LUMO, and energy difference between the valence band and the conduction band in NP and bulk solid are the most important energy scales, and they decreases as we go from atom to molecule to nanoparticle to bulk. So the color of the emitted light from different systems depend on the size of the system, the transition energy being maximum in the atom, then the molecule, and then the bulk. The transition energy in NP is intermediate between the molecule and bulk solid. So this intermediate range can be extended from visible to infrared by varying the size of nanoparticle. The top-down approach, nanoparticle as a small crystal. So in this approach, one starts from the band structure of the bulk semiconductor and the block wave functions describing the bulk properties of the semiconductor. The wave functions of electrons or holes in nanoparticles are described by the block wave function of the bulk crystal multiplied by an envelope function to take care of the spatial confinement of the charge carriers, electrons and holes and are given by psi nanoparticle equal to psi crystal multiplied by psi EF, where psi crystal is the block function for the bulk crystal and psi EF is the envelope function due to spatial confinement. So the envelope function phi E and V can be obtained from the solution of the Schrödinger equation for a particle in a spherical quantum well. So the eigenfunctions can then be best described as the product of spherical harmonics, YLM as a function of theta phi, and a radial Bessel function RR. So psi EF will be equal to YLM as a function of theta phi multiplied by RR. So the envelope function is similar to that of the wave function describing the electron in the hydrogen atom. Only difference is the potential experienced by the electron. So in the hydrogen atom, it is the Coulomb potential, that is VR, proportional to 1 by R due to proton in nucleus. Whereas in a nanoparticle, electrons experience a spherical potential well of diameter d, for which VR equal to V naught, for R less than d by 2, and VR equal to 0 elsewhere. So the solution of eigenvalues can be obtained by putting the spherical potential well in the Schrödinger equation as minus h cut square by 2 mu del square minus VR multiplied by psi EF equal to E psi EF, which gives the following solutions for the discrete energy levels of an electron confined in a E and L d equal to 2 h cut square chi square NL divided by m star d square, where m star is the effective mass of electrons decided by the band structure of the semiconductor crystal, and chi and L are the roots of the Bessel function and depends on the principal quantum numbers n equal to 1, 2, 3, so on, and azimuthal quantum number L equal to 0, 1, 2, 3, so on, corresponding to s, p, d orbitals. So the Coulombic potential in the hydrogen atom put a restriction on quantum number L, that is, your L must be less than equal to n minus 1. However, the constant potential in a nanoparticle put no such restriction on the quantum number L. Hence, the ground state of nanoparticle is n equal to 1 and L equal to 0, represented by the 1s state. And the second energy level has quantum numbers n equal to 1 and L equal to 1, represented by 1p, and the third level is described by n equal to 1 and L equal to 2, represented by 1d, and the fourth level is a 2s level corresponding to n equal to 2 and L equal to 0. Now this figure represents the energy level in a nanoparticle due to quantum confinement. In top-down approach, the band gap of a nanoparticle is the sum of the fundamental bulk band gap Eg0 and the confinement energy of both the electrons and the holes. that is EgNP equal to Eg0 plus 2h cut square chi square NL divided by Me star D square plus 2h cut square chi square NL by Mh star D square. In this analysis, the Coulombic interaction between the electrons and holes is neglected under independent electron approximation. However, under this approximation, it is not possible to have excitons in a nanoparticle. Hence, this approximation is valid if the radius of nanoparticle is less than the Bohr radius of exciton AB. Now, if we consider the Coulomb interaction taken into account, the band gap of the nanoparticle of radius d is given by EgR equal to Eg0 plus h cut square pi square by 2d square multiplied by 1 by Me star plus 1 by Mh star minus JEH plus E pole plus EH pole minus 0.248 E star Ry, where JEH represents the effective Coulomb interaction between the electron and the hole, and JEH equal to 1.786 E square by epsilon R, where epsilon is the dielectric constant of a nanoparticle. Now the term E pole and EH pole gives the self-polarization energies of the electron and hole and depends upon E square by R and on the dielectric constants of the nanoparticle and the surrounding. Here the ERY star is the exciton Rydberg energy, and this equation describes the two most important consequences of quantum confinement. First is the band gap of a semiconductor nanoparticle becomes larger with decreasing size and scales as d to the power minus 2 if the Coulomb interaction is neglected. Second, the discrete energy levels arise at the band edges of both the conduction band and valence band. So these two dependent effects are schematically shown in this figure, which summarizes the fact that the optical band gap of quantum dots can be tuned by simply changing their size. The bottom-up approach, nanoparticle as giant molecule. Another method to explain the electronic properties of a nanoparticle is based on a bottom-up approach which treats nanoparticle as a giant molecule. As it is adopted in tight binding method or linear combination of atomic orbitals, LCAO method, the total wave function of the nanoparticle can be constructed from the superposition of individual atomic orbitals. So similar approach is generally adopted in calculating the HOMO and LUMO of any molecule. Now, if we are considering the H2 molecule, which is the simplest molecule, where there is a superposition of atomic orbitals of individual hydrogen atom, and there will be two molecular orbitals known as bonding and anti-bonding orbital. So the molecular orbital are occupied by the electrons in such a way that the total energy of the molecule is minimized and normally bonding orbitals are occupied with the electrons and known as HOMO. Exactly similar approach can be applied to find out the HOMO and LUMO of the nanoparticle. Similar to large number of molecules, as the number of atoms decreases in a nanoparticle, the number of atomic orbitals increases, leading to decreasing the HOMO-LUMO energy gap or band gap in the nanoparticle. So, generally, the density of molecular orbitals is maximum at intermediate energy due to Gaussian distribution of density of states. So, there would be fewer molecular levels at lower energy and at higher energy. So, this figure schematically shows how the energy levels evolve a diatomic molecule to a bulk semiconductor. Now here EgNC and Eg0 indicates the energy gap between the HOMO and LUMO for a nanocrystal and bulk. Now in the case of compound semiconductors, cadmium selenide, cadmium telluride, lead selenide, indium phosphide, different types of atomic orbitals are combined. For example, the atomic structure of cadmium and tellurium are Kr4d10 5s2 and Kr4d10 5s2 5p4 respectively. So in the case of cadmium telluride, the LUMO conduction band comprises of the linear combinations of the empty 5s atomic orbitals of cadmium 2+ and HOMO valence band comprises of p orbitals of Te2-. So, if cadmium telluride is treated as a single molecule, LUMO will be closer in energy to the 5s atomic orbital of cadmium, while the HOMO will be closer in energy to the 5p atomic orbital of tellurium. So, this figure shows the LCAO diagram of a single cadmium telluride unit or hypothetical cadmium telluride molecule. The HOMO and LUMO of cadmium telluride molecule is obtained by bonding and anti-bonding superposition of cadmium and telluride atomic orbitals. Now, this right-hand side figure shows us the sinusoidal functions that describes the phase of each molecular orbital levels in a one-dimensional cadmium selenide nanoparticles. Now here they describe the phase of the atomic orbitals. The effect of quantum confinement on optical transitions in nanoparticles is best exemplified in their absorption and photoluminescence spectra as shown in this figure, which also shows the TEM images of the smallest, that is 2 nanometer, and largest 7 nanometer nanoparticles. In the strong confinement regime, less than 2 to 3 nanometer, the energy spacing between the discrete level in nanoparticles is in the order of hundreds of MeV, and therefore optical transitions between these levels can be clearly resolved in the optical absorption spectrum. However, in weak confinement regime, the energy spacing is typically order of magnitude less than the strong confinement regime, and it becomes difficult to resolve the transitions in absorption or photoluminescence spectra. So, as discussed before, the lowest energy optical transition can be assigned to the 1sh to 1se level, the second transition to the 1ph to 1pe level, which is clearly shown in this figure. So, scaling the size of the nanoparticle with the exciton bore radius AB is the most convenient length scale to determine the effect of quantum confinement on the properties of semiconductor nanoparticles. So, the onset of quantum confinement effects will occur at different sizes of nanoparticles for different semiconductors, as AB varies widely within the semiconductor materials depending on the effective mass of electrons and holes and dielectric constant of the semiconductors. So, through effective mass AB and energy gap EG, they are correlated. So, materials with narrower EG, they have larger AB. In the case of insulators where EG is greater than 5 electron volt, excitons are strongly localized with AB less than 1 nanometer. So, nanoparticles with 10-20 atoms may be required to observe the effect of quantum confinement on optical transitions. So, this figure shows a set of absorption spectra of three important semiconductors: cadmium sulfide, cadmium selenide, and cadmium telluride based nanoparticles of different sizes. Due to size quantization, the absorption edge shifts towards the shorter wavelengths in comparison to the corresponding bulk values, that is 480 nanometer for cadmium sulfide, 674 for cadmium selenide, and 817 for cadmium telluride. It is clear that excitonic transition is observed in all the samples, but in smaller sized nanoparticles, there are two peaks which establish that smallest sized nanoparticle indeed behave like a molecule in which absorption spectra is always doubled peak to Dadov splitting. Using these three semiconductor nanoparticles, optical transitions over a range of 300 to 600 nanometer can be covered. Even a wider range can be covered using cadmium telluride and mercury telluride systems. So this figure shows a photoluminescence spectra of cadmium telluride, cadmium X, mercury 1-X, telluride, and mercury telluride nanoparticles. It is interesting to note that optical transitions for entire spectral range from 500 to 2000 nanometers can be obtained by varying the size and composition of the nanoparticles. In particular, the luminescence spectra of mercury telluride nanocrystals of different sizes cover the spectral region between 1000 and 1800 nanometers, making them potential candidates for application as ultra-broadband optical amplifiers in telecommunications systems. Further, the quantum efficiency of luminescence of cadmium telluride, cadmium X, mercury 1-X, telluride and mercury telluride nanoparticles is quite high, 40 to 50%, making it most attractive for different applications. So students, as we have discussed before, after absorption of a photon by a semiconductor nanoparticle, an exciton is created with bound state characterized with the discrete energy levels located within the conduction and the valence bands. So, if the energy of the photon is larger than the band gap of Np, a hot exciton is formed in which the electron and the hole occupy the excited states. In such a case, the electron and the hole will quickly, that is less than 1 picosecond, relax to their ground states by means of a cascade of intra-band non-radiative transitions, mostly through by dissipating excess energy as heat. These non-radiative transitions, they are not restricted by the selection rules, hence take place very fast, either by coupling with photons or by Auger scattering. Once the exciton has reached its ground state, further relaxation can take place by electron-hole recombination. The excited electron returns to the valence band and recombine with the hole, releasing exciton energy radiatively or non-radiatively. In radiative recombination, photons with energy same as that of energy of exciton are emitted. So, in the emission spectra of nanoparticles, the direct radiative recombination of the exciton is observed as a well-defined peak with energy close to that of the lowest energy absorption transition. So, students, the effect of the nanoparticle size on the emission spectra is same as that on the absorption spectra. The peak widths of the emission spectra depends on the size and the shape distribution of the ensemble of nanoparticles. So, it should be noted over here that the emission transition in which electrons falls back from the excited to the ground state is just the reverse of lowest energy absorption transition in which electron is photoexcited from ground to one of the excited state. Therefore, the selection rules discussed above for absorption also apply for emission. So, in the case of emission transition, there is the mixing of the excited state orbital with the ground state orbital. So, the mixing is induced by the oscillating field light used for photoexcitation, which is resonant with the transition and induces the mixing, resulting in radiative recombination, which is called as stimulated emission. However, emission happens in all kinds of fluorescence systems without the stimulus of an external oscillating field, and the radiative transition is called as spontaneous emission, where mixing of the excited and the ground state is induced by so-called vacuum modes or vacuum fluctuations. So, the rate of spontaneous emission is not only dependent on the magnitude of transition dipole moment μl, μt, between the initial and the final states, and the density of optical modes that can be occupied or that can be coupled to the transition. The density of optical modes increases with frequency. So the radiative decay rate, gamma radiation, for spontaneous emission in a two-level atom system can be deduced from Fermi's golden rule, that is gamma radiation as a function of omega equal to omega cube multiplied by n multiplied by mu I f the modulus square divided by 3 pi epsilon naught h cut c cube. So gamma radiation basically depends on first the atomic orbitals through mu I f, and second the EM field through density of optical modes. Here n is the refractive index and epsilon naught is the permittivity of free space. So all optical transitions at the simplest level can be modeled as a two-level system. In optical transitions for a two-level system, an electron is excited from the ground state orbital 1 to an excited state 2. So excitation process can be represented by the mixing of the ground state and excited state into a mixed state, which is psi is equal to C1 1 plus C2 2. Dipole moment and optical transitions in nanoparticles. So this figure schematically shows what happens when different orbitals with different phases are mixed. So a symmetric mixed state results without a dipole moment when the two orbitals with the same parity are mixed. So mixing of these orbitals cannot be induced by an oscillating electric field. On the other hand, an antisymmetric mixed state results with a dipole moment when the two orbitals with different parity are mixed. So in this case, mixing of these orbitals can be induced by an oscillating electric field. So here, when two s or two p orbitals are mixed, a symmetric wave function results without a dipole moment, and the mixing of the s and the p orbital. In the case of cadmium selenide nanoparticle, this involves a transition from the MO formed by the linear combination of selenide 4p orbitals to MO formed by the linear combination of cadmium 5s orbitals. So within each unit cell, mixing of these states yields a dipole moment, which is indicated by the small arrows in this figure. So the direction of the individual dipole can be deduced from the previously discussed figure. So when the individual dipoles adds up to a net dipole, the optical transition is parity allowed. If they cancels out, the transition is parity forbidden. In this case, as all the atomic orbitals are in phase, all the dipoles of the individual unit cells points in the same direction, which results an asymmetric electron density distribution in the nanoparticle when the 1 selenide and 1 Pe levels are mixed, giving rise to a net dipole, making the transition parity allowed. So students, let us summarize what we have learnt in this module. First, we discussed that due to quantum confinement, which can be understood via two different approaches, that is top-down method and bottom-up method. Second, the HOMO-LUMO energy bands of cadmium telluride nanoparticles have been discussed in detail. Third, we have discussed the effect of quantum confinement on optical transitions in nanoparticles. Next, the absorption and photoluminescence spectra of semiconductor nanoparticles has been discussed. Lastly, we studied the dipole moment and optical transitions in nanoparticles. Thank you.